So I'm going to put one big box on this expression here. And instead of G lambda comma observed, I'm going to substitute alpha lambda. Okay? So that alpha is alpha lambda, G lambda, D lambda, D lambda. This is the second expression. So my question to you now, we have 5 minutes for 2 questions. First question, under what circumstance can I say that epsilon is the same as alpha? Look at the 2 integrals in the big boxes. Under what circumstance can I say that the first big box is equal to the second big box? Yes.
Thermal equilibrium, so that lets us figure out E and G equal each other.
That's absolutely right. So if I am in a situation where the surrounding is an ideal body at the same temperature as the surface, that's the first condition. Obviously that's what we used at the beginning, right? So when surrounding is ideal and at same temperature as the surface, which is thermodynamic equilibrium, then I can say that G lambda is the same as E lambda comma B, and obviously the 2 integrals will be the same because I'm already operating under the assumption that epsilon lambda is equal to alpha lambda. Okay, those are the assumptions that we already have listed here. This is true. Using that and using either the case that the surface is diffuse or the irradiation is diffuse, this is true. If these 2 are true, when is alpha is equal to epsilon? Thermodynamic equilibrium, fantastic. What's the second situation? Could you do something to this integral here such that I can take this out? If E epsilon lambda does not have a dependence on lambda, and if alpha lambda does not have a dependence on lambda, but if epsilon lambda does not have it and if epsilon and alpha are the same, then obviously they're not going to have it. And so this is called as the case of a surface being gray as the color, which means that the absorptivity and emissivity are independent of the wavelength. Okay, so this is the next situation. So when alpha lambda, which is equal to epsilon lambda, is independent of wavelength, this is called as a gray surface. And so you have all these following cases. If my surface is diffuse and if the surface is gray, which is the approximation that we used at the beginning of the semester, then we can say that alpha is equal to epsilon. If the surface is diffuse but it is not gray, all hell breaks loose. Alpha is not the same as epsilon, but we at least have this case being the same. Alpha lambda is equal to epsilon lambda. Or I could have the following: if the surface is not diffuse but if the irradiation is diffuse and if the surface is gray, I can have epsilon is equal to alpha. So I have a lot of cases that I can select and tailor our problem so that some of these equalities hold true. And this is typically tailored to be such that I don't need to rely on thermodynamic equilibrium. This is very strong. It is highly impractical and it's not worth our time investigating that, but if you're doing quantum mechanics and so on, that becomes a little more predominant in such situations. for us as practical engineers, most of these are going to be properties of surfaces, and so that's what we would be looking for. So for us, we would like to have a surface that is diffuse, a surface that is gray for epsilon equal to alpha. If the surface is diffuse but not gray, that's the case. If the surface is gray but not diffuse, then I have to strictly be in thermodynamic equilibrium, or I have to be in diffuse irradiation for alpha to be equal to epsilon. Okay, so what I'm going to do on Friday, and you're going to have a problem on this particular aspect on your exam. So on Friday, I'm going to summarize all these cases with a very quick table, and then we're going to solve a couple of problems to get used to this idea. Okay, thank you.
We left off